All right, in this video, we're going to introduce transforming functions and, in particular, transforming the graphs of functions. So we're going to have some parent functions that we deal with in many of these examples, which a parent function is just a very basic function where there's no transformations applied to the function. So here we have the graph of y equals x. We could also say f of x equals x. Here we have y equals x squared, or f of x equals x squared. Here we have y equals x cubed, or f of x equals x cubed. Here we have y equals the absolute value of x, or f of x is the absolute value of x. Here we have our square root function, y is the square root of x. And here we have our cube root function, y is the cube root of x. Again, we could replace the y's with function notation as well. So in this video, we're going to take a look at vertical and horizontal shifts. So before we do that, though, we're going to look at the graph of the function absolute value of x. So it's the one that looks like a v. And we're going to see what happens when we take that absolute value function and add or subtract a real number to it. So here, I have our absolute value graph, and if we hide the g of x function, and I'm just using these subscripts for, so I can use f and g over again, but call them different subscripts. But here we have the absolute value graph, and here's where you're not adding anything to it. Well, if we add a positive number to it, so here's in red or in blue, it's the absolute value of x and then plus 1. So we see how the graph in red is transformed if we add 1 to the function itself. So absolute value of x and then plus 1. And as we increase the value that we add, notice our graph is moving upward. So for instance, in blue here, we have the graph of the absolute value of x and then plus 4.5. So we can take a look at these points here and see what happened with our original function in red. And now if we reset this back to 0, now let's see what happens if we subtract a number. So in blue, we have the absolute value of x and then minus 1. So absolute value of x and then minus 1. That's our graph in blue. Our graph in red is still our parent function. And as we subtract larger numbers, look at where the blue graph is moving in relation to the red graph. So here's the graph in blue of absolute value of x and then minus 4. Again, our red graph is our absolute value parent graph. So a vertical shift, or also known as a vertical translation, is going to move each point on the graph either up or down by a given number of spaces. And in this case, it's going to move the graph up or down based on whatever we're adding or subtracting outside of this absolute value bars. So in other words, if we're adding a number like plus 3.4 or 3.3, it moves the parent graph up that many spaces. If we subtract, it moves it down. So vertical shifting or vertical translations move the graph up or down based on whether you're adding or subtracting a number outside of that function. So again, if it's f of x plus a number, it's going to move the graph up. In other words, we're adding that number to all the original y coordinates. And if it's f of x minus a number, we're going to move the graph down. We're subtracting that number from all the y coordinates. So example 1, for each, list the parent function and indicate the vertical translation. Be specific, so I need how much it was translated in what direction. So we have g of x is x squared plus 3. Our parent function is going to be x squared. So I believe there were about 6 of them in the beginning. The parent function for this one is x squared. So we can actually make this x squared for our parent function, and we can make this x squared plus some number. So we're going to start with x squared plus 3. So we'll change d to 3, and the graph in blue is x squared plus 3. The graph in red is our parent graph, x squared. Well, hopefully you can see that it takes this x squared graph in red and moves every point up a total of 3 spaces. So for instance, on the original graph, we had negative 1, 1, and on the new graph, we have negative 1 and 4. So right there, well, close enough. So this one moves everything up 3 units. This one, g of x is x cubed minus 2. Our parent function is x cubed. The minus 2 at the end indicates we're going to move everything down 2 units. Finally, part C, g of x is the absolute value of x plus 4.7. Our parent function is absolute value of x, like we saw earlier, and then it's going to shift everything up 4.7 units. All right, so that's what happens when you add or subtract outside of the function, so outside of these absolute value bars or outside of the squaring. But now we're going to look at what happens as you add or subtract inside the function. So let's take a look at what happens as you add or subtract inside the function. So right now, here's my parent function, and I'm subtracting 0. So if I subtract a positive number like x minus, let's go x minus 3, notice the C is inside the absolute value bars. The original graph's in red. If I subtract 3, it moved my points 3 spaces to the right. So all my original points are now 3 spaces to the right. And as I subtract more and more, I actually move further to the right. So subtracting a number inside the function moves your graph to the right that many spaces. Now, if we change this to minus a negative, so well, let's just change this. Change that to a plus, and we'll reset C to 0. Okay. So now, if we, let's say, x plus 2 inside absolute value bars, notice it took our original graph and moved each point now 2 spaces to the left. And as we increase the number we're adding, it moves it further to the left. So now it moved this 0.3 units to the left. So when we add or subtract a number inside the function, that's called a horizontal shift or a horizontal translation. So it's going to move the graph left or right based on the number of spaces. So if it's x plus a number, it's going to move the graph left that many spaces. If it's x minus a number, it's going to move the graph to the right. So it's the opposite of where we normally associate our positives and negatives on the x-axis. To give you a better understanding of this too, if you are facing somebody and you point your index finger to the left, you're pointing to the left, but from their perspective, you're pointing to the right. So when you switch perspectives for pointing left or pointing right, it switches the direction in which it looks like you're pointing. If you point up or down, like vertical translations, if you point your finger up, index finger up, got to clarify that. If you point your index finger up to the sky, from your perspective and your friend's perspective, you're pointing upwards. Likewise, if you point downwards, from both perspectives, you're pointing down. So with left or right, it's actually counterintuitive. Up and down, it is intuitive. So again, with horizontal shifts, your addition and subtraction is done inside the function. So you're going to need to use parentheses for functions that have powers like x squared and x cubed. All right, example 2, for each of the following, list the parent function and indicate the horizontal translation. Be specific. So we have g of x is x minus 2 in parentheses squared. So our parent function is the squaring function. F of x equals x squared. So let's just go ahead and change this because we can. It's my video. I'll do what I want. And inside, we'll have x. Let me get rid of this. Can't remember what it was. Minus 2. Whoop. It always does that. So notice we take our red graph, the parent function f of x, and now with x minus 2, we actually shift our points 2 spaces to the right. So again, minus goes to the right, plus goes to the left. So it's a horizontal translation, shifting right 2 units. Part B, absolute value of x plus 3. Our absolute value of x is our parent function. The plus is inside, so it's going to move the graph to the left 3 units. And part C, g of x is the square root of x minus 6. This time we have the square root function as our parent function, and a minus 6 inside means we're shifting our graph to the right 6 units. All right, that about does it for this video. Thank you for watching, and I'll see you